Now in this class we would be looking into electronic configuration, right, based on our previous lecture, based on the rules of filling up orbitals with electrons, right, which are of Bohr principle, your Pauli's exclusion principle, and your Hund's rule of maximum multiplicity, right. So while writing the electronic configuration, we need to make sure that we are filling up orbitals based on these three principles, right. Now after looking into electronic configuration, we would be looking into some exceptional electronic configuration, right, that will not follow this order, because we said that as per of Bohr principle, the distribution of electrons in orbitals should be in increasing order of their energies, and the increasing order of energy is this, like 1s is lowest, then 2s, right, then 2p, 3s, 3p, 3d, in this order, right. But in certain exceptional cases, like the electronic configuration of copper and chromium, we will see that the order is not as per this order, right. The filling up of orbitals is not as per this order, right. What is the reason? We'll look into that, right. So first, what is electronic configuration? Electronic configuration, we know, is it's simply the filling up of electrons, right, in various orbitals of atoms based on of Bohr principle, your Pauli's exclusion principle, and your Hund's rule of maximum multiplicity, right. And there are certain exceptions in this order, right, that we would be seeing, right. So what is electronic configuration? Electronic configuration is filling up of orbitals of an atom based on of Bohr principle, right, Pauli's exclusion principle, right, and your Hund's rule. Right. Of Bohr principle tells us to follow this order, right, to fill up orbitals with electrons, right. We'll first fill up electron in 1s, then 2s, then 3s, 1s, 2s, then 2p, then 3s, 3p, 3d. In this order electrons would be filled, right. And what is the maximum number of electrons that these orbitals can occupy? That depends on the azimuthal quantum number, right. How? S, right, for S, the azimuthal quantum, for S orbital, azimuthal quantum number is 0, right. That means it is only one orientation, one orbital, and one orbital can occupy maximum of 2 electrons, right. This is how we show orbital, right. Why I am using this opposite arrows, right? Why I am using this opposite arrows? This is because of your Pauli's exclusion principle, right? Because Pauli's exclusion principle said that when you fill electrons, right, in an atom, in an orbital, right, these should have opposite spins. The electrons in an orbital should have opposite spins, right, because no two electrons in an orbital can have set of 4 quantum numbers same. The spin quantum number will always be different, right, and these two electrons will have opposite spins. That is, one is spinning in anti-clockwise direction, the other is spinning in clockwise direction, right. And Hund's rule of maximum multiplicity, what this rule tells us? This rule tells us that we should have maximum half-filled orbitals, right, and they should have parallel spins, right. This is what this rule tells us. This tells us maximum half-filled orbitals with parallel spins. And how this arrangement would be helpful, because if we know that in two electrons are similarly charged, they have negative charge, So if they are in the same orbital, there would be maximum repulsive force, right? So the practice is that to distribute these electrons in different orbitals, right? Then you start pairing up. Once all the orbitals are finished, right, with 1 electron each, then you start pairing up electrons, right? You will not start pairing up of electrons unless all the electrons have orbitals have 1 electron each. All the orbitals are half filled. Once all the orbitals are half filled, then start pairing up, right? So minimum inter-electronic repulsion, right, with half filled orbitals, and same is the reason for parallel spins. We have minimum inter-electronic repulsion, right? So let's look at the electronic configuration of hydrogen. We know that hydrogen has atomic number 1, right? So if you look at this, atomic number 1 means it has 1 electron, right? So only one first orbital will start filling up with 1s. The electronic configuration would be 1s, right? 1 represents the principal quantum number, that is the first shell, and s represents the s orbital, right? And 1 represents your electron, 1 electron. This is the general notation, right? This is the general notation, or you go by this. Either NLX means your S to the power of A, right? SP to the power of B, then D to the power of C. SP, D are orbitals, right? A, B, C are, which are in superscript, are number of electrons, right? And N here represents your principal quantum number, which is the main shell. If I put 1 here, first shell, if I put 2 here, this second p orbital of second shell, right? So either you write electronic configuration in this box, in these boxes, right? One box represents 1 orbital, right, and can contain maximum of 2 electrons. Similarly, if you have say helium has atomic number 2, so electronic configuration would be 1s2, right? Now the other is hydrogen, helium. Then you have lithium, right? Lithium has atomic number 3, right? So electronic configuration would be 1s2, 2s1, right? This is the electronic configuration for lithium, 1s2, 2s1. And if you want to show this in box notation like this, it would be like this. This is up and down as per Pauli's exclusion principle. Then I'm filling up first 1s, then I'm filling up 2s. Why? Because as per Aufbau principle, we have to follow this increasing order, right? Now let's look at some other elements. Let's look at boron, right? Boron has atomic number. Boron has atomic number, it's I think it's 6 or 5. Boron has atomic number 5, right? So we have to distribute these 5 electrons, right, based on this sequence, right, in different orbitals. So first we'll go in 1s2, second is 2s, s has maximum of 2 electrons, then again 2s2, then you have 2p. How many remaining electrons? 1. So 2p x1. Why I am putting x? Because we know that p subshell, right? For p subshell have 3 orbitals. 3 orbitals, that is px, py, pz. How we reached at this conclusion? For p, for p, L is equals to 1, right? This is the value of azimuthal quantum number for p subshell, right? So these px, py, pz are what? These are orbitals which are your orientation of p subshell in different directions, in 3 dimensions, right? That is orientation of these orientation of p orbital in x-axis, y-axis and z-axis in 3 dimensions, right? These 3 orbitals represent the orientation of p orbitals in 3 dimensions. So how do we know that it has 3 orientations? Based on magnetic quantum number, because as per magnetic quantum number, 2l plus 1 orientations, right? We have 2l plus 1 means 3, right? So we have 3 orientations as per the magnetic quantum number, which is in 3 dimensions. In px is along x-axis, right, and py is along y-axis, right? So you have these are the 3 orientations which are given by magnetic quantum number, right? 2l plus 1, 3 values, that is from minus L to plus L, right? Minus L is your 3 orientations, and you give it like this: 3 orientations, right? Minus L to plus L. Minus L is minus 1, 2 plus L, 2 plus L including 0. These are the 3 orientations. This value of 2l plus 1 will tell you the number of orientations. Minus L, this value of L, that means minus 1 to plus 1, right? This will tell you the 3 orientations. These are the 3 orientations, right? So I wrote 2px, right? So if we want to write this in box notation, it would be like this. This represents 1s, 2s, then you have 2px, 2py, 2pz, right? We have 1 electron left which will go in 2px. It may go in 2py, in 2pz, because these 3 orbitals are degenerate orbitals. They all have same energy. So doesn't matter electron is in 2px, 2py or 2pz, right? So now let's look at one more. Let's look at the electronic configuration of oxygen, right? Electronic configuration of oxygen is, the atomic number is 8, right? Atomic number is 8. So you have to distribute 8 electrons as per this sequence. It would be 1s2, 1s2, 2s2, right? Then 2p, 4, 1s2, 2p, it's 4, 2px1, 2py1, 2pz1, right? And then you have 3s1, right? I'm sorry, this is I'm sorry. This would be like this. I'm sorry. It should be, since each orbital can have 2 electrons, right? So 1 electron. First we will distribute 1 electron as per Hund's rule of maximum multiplicity. Once all 3 orbitals have 1 electron, once all the 3 orbitals are singly filled, then we will start pairing up the orbital. It would be 2 here. This is the perfect example to understand your Hund's rule, right? Let's just do it in box notation to understand it. This is 1s, right? And this is your 2s. Then is your, we have 4 more electrons to distribute, because atomic number of oxygen is Z is 8. So 8 electrons, 4 are distributed. So we have 4 more electrons. We have now Hund's rule of maximum multiplicity is followed in the orbitals of same subshell. Here it's p subshell. These are the orbitals of p subshell px, py, pz, right? So first I will distribute 1 electron, right, to each of these orbitals, because singly filled orbitals have minimum interionic repulsion. And why I'm giving all three of them same direction, right? They have parallel spins. Same direction means they have parallel spins, because parallel spins will contribute minimum electronic repulsion. I'm sorry, right? Once all these have one electron each in each of these orbitals, then I will start pairing up. This is what Hund's rule says. First, each of the orbitals should have one electron, should be half filled, then start distributing electrons, start pairing up electrons. And I started pairing up. I gave one electron to 2px, right, as per Hund's rule, right? And as per Pauli's exclusion principle, I have added the electron with opposite spin, right? Because no two electrons can have four quantum numbers same, right? Spin quantum number would always be different. One is anti-clockwise, the other is clockwise, right? So this is your oxygen electronic configuration, right? Now suppose you want to write electronic configuration. Suppose you want to write electronic configuration for some ions, right? Let's say hydrogen ion. If you remove one electron from hydrogen atom, it will become a proton, right? We know this for a long time now, right? Now, what is the electronic configuration of proton? It's 1s. It's 1s0. If you look, the electronic configuration is 1s1, right? If I am removing one electron to make it proton, the electronic configuration would be 1s0, right? And what would be the electronic configuration of oxide, right? O2 minus, right? Electronic configuration for proton is H plus. I have removed this electron. Electronic configuration would be 1s0, right? This is your cation, electronic configuration for cation, right? Now what would be the electronic configuration for anion? Anion of hydrogen is hydride, right? So if I add one electron, this will become hydride. It would be, adding one electron will make it 1s2. This is the electronic configuration for hydride. We have understood this oxygen, electronic configuration for oxygen. Now what is the electronic configuration for oxide ion, right? Oxide ion is, how will you represent oxide ion? It's O minus 2, right? It has two electrons. Why minus 2? Why it can accommodate two electrons? Because it has two half filled orbitals, right? Px, Py and Pz. Py and Pz. So electronic configuration of oxide ion would be, how many electrons will this oxide ion contain? It already had 8 electrons. So 2 minus means it had gained 2 electrons. When it will gain 2 electrons, plus 2 is equals to, it will have 10 electrons. Now this is for oxide ion, right? Now 2 minus oxide ion, I need to distribute these 10 electrons. 1s, then here is your 2s, right? Then here you have right, so 2 electrons, one will go in this orbital, one will go in this orbital. This is the electronic configuration for oxide ion, right? So this is how you will write electronic configuration following Aufbau rule, Pauli's exclusion principle and Hund's rule of maximum multiplicity, right? Now we will look into one important thing of some exception electronic configuration, right? We will look into the exception electronic configuration of copper and chromium, right? Exceptional electronic configuration of copper, right? Copper, for copper the atomic number is it's 29, and for chromium it's 24, right? Let's first look at chromium. It's chromium, the atomic number is Z is equals to 24. Then copper we have Z is equals to 29, right? Why we say exceptional electronic configuration? Because electronic configuration of chromium and copper does not follow this sequence, right? And what is the reason that it will not follow this sequence? We will look, right? First we will write the normal electronic configuration based on this, right? Based on your sequence. It will be 1s2, 2s2 till 4s. We need to write this, right? Z is first we will see for this. It's 1s2, right? Then you have 2s, then you have 2p, right? 2p, 2px, 2py, 2pz, right? Then you have 3s, right? Then again, then after 3s you have 3p, which is your right? Then after 3p you have 4s. I'm sorry, it would be this is your this is your 1s, 2s2, then you have 2px, 2py, 2pz, then you have 3s2, right? Then you have 3p6, right? It should be 3px, 3py, 3pz, right? You have 3s, you done with 3p, then you have 3d, right? You have 3d, and in 3d we can have maximum of electrons. In 3d, right? 3d, right? How many electrons? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18, right? 19 20 21 22, right? And we know that d has 5 orbitals, right? Then you have 2 electrons left, right? So 2 electrons will go to, after 3d you have 4s, 4s, right? Now as per the, what is the exceptional here, right? This is the normal configuration, right? This is how we write the normal configuration. So as per the exceptional configuration, the electron from 4s, right? Electron from 4s will shift to d orbital of chromium, right? This is the d orbital which is empty, right? So electron from 4s will move to d orbital, right? That is of lower energy, from lower energy to higher energy. This is what is exception, right? An electron will shift from a subshell of lower energy, right, to a subshell of higher energy, right? We know that d is a subshell of higher energy. If you look at the energies of orbitals, it is s is greater than p is greater than d. Sorry, s is less than p, then p is less than d, right? This is the order of this is the order of energy of orbitals, right? So here the exceptional is normally the electron will occupy the orbital of lesser energy. So here what is happening is electron is getting shifted, right, from lower energy to higher energy orbital. S is your lower energy orbital, right, and D is your higher energy orbital, right? So one will shift from here to here, and this will lead to the stability, right? So why it will lead to the stability? Why it will lead to the stability? Because of, if we write it like this, this will remain like this. So one electron, this is your D4, right? This is a D4 atom. So electron will shift, right? And this will be 4s. Earlier it was D4 4s1. Now it will change to D5 4. I'm sorry. It was D4 4s2. Now it will change to D5 4s1. So this electronic configuration is stable compared to this, right? What is the reason? The reason behind this is, first reason is your symmetry. Right, here you can see that when I shifted an electron from 4s to this 3d, 4s to d orbital, from s orbital to d orbital, it lead to the symmetry. You can see now all these orbitals look alike. All these orbitals have one electron, right? So this has, by shifting electron from 4s orbital of, that is orbital of lower energy, to orbital of higher energy, we have achieved stability. And we know that stability always contribute, when we transferred electron or shifted electron from 4s to d orbital, from lower energy to higher energy, it lead to more symmetry, right? So symmetry has increased, and we know that symmetry will add to stability, right? So due to symmetry, because the symmetry has increased, right, that will increase stability, right? This will add to stability, right? Because of symmetry, stability has increased, right? So the distribution of electron will become more symmetrical, right? When we shifted the electron, the distribution of electrons has become more symmetrical, right? That will add to, or that will impart symmetry, right? It will impart extra stability. Sorry, this symmetry will impart extra stability. Therefore, electronic configuration of chromium as given above, right? As given above means this one, D24S2 is wrong and this one is right, right? So symmetry will add to the stability, right? And the second reason is your exchange energy. Second reason is exchange energy. When you have maximum of unpaired electrons like this, they can exchange these electrons, right, half filled or fully filled, right? They can exchange their positions, and when they will exchange their position, energy would be released, right? And once energy is released, they will attain stability. That is, this can exchange position with this, with this, with this, with this, right? So due to this exchange of energy, due to this exchange of position of electrons with parallel spins, the stability will increase. Similarly, this can exchange energy with this, with this, with this. Similarly, this can exchange energy, its position with this, right? So due to this exchange of position, right, between these electrons of parallel spins, right, it will release energy, and release of energy will add to stability, right? So these are the two reasons why we will write why the electronic configuration of chromium is D54S1, 3D54S1, not this, right? So this is an exception. Same is the reason with copper, right? That has atomic number 9, right? Same is the reason for copper, exactly same reason, right? The symmetry